and welcome to episode number 9 of CS350 Online. I'm your host Leslie, and in today's episode we are going to answer that cliffhanger question from our previous episode and figure out how on earth do user programs and the user actually interact with the kernel and its data structures. But first, a couple of announcements. First is that assignment 2 is actually posted now, and you can get started whenever you like. Now, assignment 2 is actually a bunch of other assignments that have been recombined together, so we apologize in advance if there's some language that may be unclear and are still typos in it. So please do let us know if you find anything that's left over from that. The other thing I want to say is we will actually go over in episode 11 how to actually do assignment 2. So we'll talk about all the different things that you need to do and kind of a high level how to approach assignment 2 in episode number 11. So that will be next Tuesday. All right, so I want to apologize to you in advance if you see me running from my desk. I am going through a bit of morning sickness, so hopefully I won't act up, but I don't really have a lot of control over that, so we'll see what happens. All right. So, first, our OS of the day before we get into our cliffhanger. That's not the OS of the day. There it is. So the OS of the day is Unix, sometimes spelt with a C instead of an X. And what is Unix? Well, this is an operating system that was developed around 1969 to 1973. And this was a product of Bell Labs. And what ended up happening was there was a whole bunch of people who were working on Multics who were a little bit disgruntled with how Multics works. Disgruntled is probably the wrong word to use. But the idea was that it was some old Multics developers like Richie and Ken Thompson. And they actually went off to Bell Labs and they started to create their own operating system, because they felt that Multics was way too heavy, it was too complex, and they wanted something that was a bit simpler and smaller and easier to work with. So they went and created Unix. They also wanted to make sure that their operating system was portable, that is, you could take it from one kind of hardware to another. And you'll notice that this is the first operating system where we have it at the very top actually specified what hardware it ran on, and that's because Unix was designed to be portable and able to run on multiple different kinds of hardware. So, what does Unix have? Well, what doesn't it have? So, it was a portable operating system, it supported multiple users, and it had preemptive time sharing. And it did something similar to Multics, so it did things like treating things as files, but it went a step further to treat everything as a file, even devices. So if you're a Unix person, you can actually access things like the serial port as if it was a file. So the serial port's usually TTY0, and so if you try to read or write from TTY0 or dev/TTY0, then you would actually be trying to read or write from the serial port, and that's actually really neat. They also had inter-process communication, was being treated as files, so it's a pretty neat system. They had a hierarchical file system, which wasn't necessarily new, but it was something they supported. But they also stored data as plain text instead of in some kind of proprietary binary format. And another major feature that Unix brought to the table is instead of having one specific program for each task, they actually had this concept of pipes where you can string a bunch of smaller programs together and have the output of one program become the input of the next. So for example, if you wanted to show all of the processes that were Chrome, before Unix you would have to create a specific program just to do that task. But with Unix, you can pipe the output of PS to grep and it will do that same task for you. So that was actually a pretty powerful thing. And of course, there's many other features. Now, if you want to know more about Unix, you could go and I think it's episode 8 or 9 in the spring of 2020, we actually had Dr. Brian Kernel, who worked with Richie and Thompson at Bell Labs, and also is the author of many famous books that you may have known, The K and KNRC. He actually gave a little interview for our class back in the summer, and you're welcome to go look at that video if you want to know more about it. Now, I want to show you kind of the influence that Unix has had because it's pretty big. So if we have Unix up at the top here in 69, and this chart is so incomplete, what you can see here is all of the different operating systems that are either Unix-like or are derivatives of Unix. So for those of you who have a Mac in front of you right now, you are this kind of peachy box down here, and it goes from Unix to BSD, BSD to next step to Mac OS X Server, and then to Mac OS X. And then you've got your free BSDs, which stem from Unix system, or Unix version 5 and 6. And then you've got SunOS and Solaris also coming in from BSD. You've got the Xenix, SCO versions, AIX. You've got Open Server. You've got Unixware, all of those kind of stemming in from about Unix version 7. So many different things here. And then Minix and Linux, they don't share code from Unix, but they are Unix-like operating systems in that they share a lot of the same ideas that the Unix OS actually does. So Unix has had a huge impact on the world today. Very important OS. All right. So where did we leave off last day? So last day, and I know it was like last week, so nobody remembers what was happening. We were talking about process management calls, and in particular, we were talking about things like fork and wait PID and get PID and exec v, and what their different jobs were. So remember, fork creates a new process. Let's actually just scroll right up here. So we've got fork to create a new process, which remember it creates a cloned process. So we're making a new process. It has its own PID and its own address space, but the contents of the address space are identical to the address space of the parent. Exec v, it doesn't create a new process. It takes the existing process and changes the contents of the address space so that it is running a different program. So a process that was once running Hello World is now running MATLAB. And then we have exit, which terminates the calling process. And if you have a living parent, you'll leave behind some information so that the parent can know why you terminated, should they make an inquiry about are you terminated or not. And it works hand in hand with wait PID, which is going to, if you want to wait for a process to finish, and remember, you don't have to wait for a process to finish. But let's suppose you wanted to wait for a process to finish. Wait PID is the way to do it. You would wait for one of your children to finish, and when they finish, you would get their information about why they terminated and any messages they left behind. And then get PID, of course, just returns your PID. Now, we went over these in greater detail, and we'll be going over all of these functions actually in even greater detail in episode 11, where we talk about how to implement assignment A2. But all of those were actually just examples of system calls. So system calls are calls where we're asking the kernel to do some task for us. So for good abstract design reasons and also for security, we don't let user programs or users directly access things like the file system. We don't let them directly alter the voltage of the CPU without the kernel of the operating system being involved, because number one, the implementation may change as we start to do bug fixing, and number two, one of the other things that can happen is that if the user can actually directly access the file system, then number one, their code will have to be very specific to the hardware, which isn't a good abstract design. But moreover, one of the problems we're going to have is that the user program will be able to bypass any permissions that the kernel might have been enforcing on the file system. So it's a bit of a security breach to let the user programs access this kind of thing. So the kernel of the operating system provides a bunch of system calls that you can use to ask the kernel to do a task for you. And process management calls like fork and exec v are examples of those. But then we talked about this concept of privilege and how things that are running, there's two versions of privilege. There's unprivileged and privileged code. And unprivileged code is things like your user program, but it also includes the system call library, i.e. the fork and exec v functions. And this is not just some logical separation. This is actually a CPU level separation where kernel code is only permitted to run in privileged mode, which is actually a physical mode on the CPU. And user applications in the system call library are actually only permitted to run in an unprivileged state. So they've actually separated from each other. So the user program can't access the kernel's data structures. The user program cannot call the kernel's functions. So we've isolated these two things from each other, which left us with this question of how on earth do you as the user actually call or access any of the kernel's functions or data structures? Interesting problem, isn't it? So the answer to the cliffhanger, by the way, let's move over to our new content. There we go. Is we're going to take advantage of interrupts and exceptions. Because realistically, if we want to force the kernel to run, that's the only way that we can do that. So remember that interrupts are things that are generated by devices. So if I click a button on my mouse, that's going to be a hardware interrupt. That's going to be a signal sent from my mouse to my CPU to say, hey, the mouse requires attention. Exceptions, on the other hand, are caused by an instruction that is executing. So for example, if you were dividing by 0, that is a program that requires some assistance. Now, remember that when we're dealing with interrupts, again, it's hardware. And what happens when the CPU receives that signal of an interrupt? It's going to say, okay, so what we need to do now is, since I don't know what to do with the interrupt, I need to ask the kernel to handle this interrupt for me. So in the trap table of the CPU, it will know exactly the address of the interrupt handler for the kernel. And so when the CPU receives that interrupt, it's going to start executing the interrupt handler for the kernel. And then the interrupt handler, of course, will save the trap frame and then figure out which device actually threw that interrupt, and then we'll actually call the appropriate functions from there. Not too bad, right? And exceptions, similarly, even though they are happening due to code that's executing, the same rough idea is going to happen. Is when an exception is detected by the CPU, we are going to use the trap table lookup to find where's the address of the exception handler. And at the point where we are executing kernel code, where actually the CPU is going to switch itself into privileged mode so that the CPU can actually execute that interrupt or exception handler on its own. All right. So here's a couple interesting things about MIPS. So first off, in MIPS, everything is an exception. MIPS doesn't actually differentiate between interrupts and exceptions. So everything in MIPS is an exception. And there are different kinds of exception types to indicate what's actually happening. So for example, EXIRQ, IRQ is... it's the short form for interrupt, and I don't know why it's the short form for interrupt. It just always has been since I was a kid. If you have an EXIRQ exception type on MIPS, that means you actually have a hardware interrupt. And then you've got some other ones here. You've got TLB miss on load, TLB miss on store, which you may have come across those if you've started working on assignment A2. And then you've also got things like address errors, bus errors, arithmetic overflow. And then the one we are going to make use of for interacting with the kernel is exception 8, exsys for syscall. Now we have a question on Twitch. Can running in privilege mode be spoofed? So here's an interesting thing. So you've heard me mention before that the CPU rearranges instructions. And it does it because it's trying to improve the performance of the code that it's going to be executing. So your standard Intel chips, this is something that they actually do. And here's the problem. When it rearranges instructions and it starts putting them down the pipeline, some of the instructions that may get executed might be instructions for privileged mode. And because these are instructions that we didn't actually need the result to just yet, what happens is, let's say you're loading something from an address that only the kernel should be allowed to see. Because the CPU has actually rearranged them, that data might end up getting retrieved and cached before you actually use it in a privileged state. And what can happen is you can do a timed cache attack to actually get that data out, that privileged data out of the cache while you're still running in unprivileged mode. This is actually the Meltdown bug, by the way. I will post a link to both the Meltdown and the Spectre papers. They are finding ways to get around this privilege mode to steal information from the kernel. And it's been a pretty big problem for Intel. And my understanding is they've released a fix for it, but it actually comes at a cost of performance, which makes sense because we were reorienting the instructions for performance reasons. So if you want to know more about those two bugs, I'll post a paper. Now, if you've never read anything about security, don't be afraid. I actually find that the two papers are actually quite approachable, even if you have never read a security paper before. So I'll post those two papers to Piazza for anyone who's interested. All right. So for our purposes, we are going to use this exception number 8 syscall to actually tell the kernel that, hey, we want you to execute an instruction on our behalf. Okay. So, what I want to do is I'm actually going to switch over to OneNote here. So instead of reading these slides, I'd actually like to just draw out what we need to do. And then I'm going to show you all the code that does it. Because that's a little more fun, right? All right, so try to connect my little tablet here. There we go. All right. So what you're going to do in order to actually communicate with the kernel of the operating system is inside the implementation of fork, or whichever system call library function you're working with, you are going to need to raise the system call exception. And you can do that with an instruction called syscall. And it raises the exception. So that's fairly straightforward. But obviously there's lots of different kinds of system calls. So how do we choose which system call we're actually going to use? Sorry. Told you my morning sickness makes me so I'm not feeling the greatest right now, and mint candy canes are helpful. So, my apologies. All right. So, what are we going to do? So, we've got the instruction now to raise the system call exception. But how do we tell the kernel what we want it to do? Well, obviously, we're going to need to tell the kernel in some way via a register which system call code or which system call we're actually wanting to use. And we're actually going to put that into register V0. And this is to tell the kernel which system call. All right. Now, how do you know which of these? I called them system call codes. How do you know what those are? Well, let's go over here into the kernel. So inside of the include directory, you'll see a directory called kern. Go in there. And inside kern include kern, you'll see something called syscall.h. And what you see in this file is actually the system call codes for all of the different system calls that we can support in OS 161. And you'll see that there's a lot of them. So here we're at the very top, we've got the ones for process management. Then we've got virtual memory, security ones, signals, groups related to file handles, paths, symbolic links, mounting, files, ownership of files, file system, shutdown, sockets, time, you name it. All of those things are now in here. Now, a question on Twitch is, why are some of these commented out? Because they're not currently supported in any way, shape, or form in OS 161. And in fact, if you look here, there's actually a lot missing. So there's no system calls to create a thread because OS 161 doesn't actually support the user programs actually creating more than one thread. So for all of our test programs from here on out, each program has only one thread. You don't have to worry about multi-threaded programs. Now you just have to worry about having multiple processes. All right. So you're going to learn that fork is actually system call code 0. And then when you go back to implementing your implementation of fork, you would put into register v0 value 0. Because that is the system call code for fork. Now that part of the kernel, that whole directory, kern include kern, is actually called the kernel's application binary interface, or ABI. It's the information that the kernel is willing to share with the user program. There's nothing secretive in there. It's the bare minimum of information we need to pass on to the user program and the system call library, which runs as a user library, in order to actually interact with the kernel. But is that everything we need? Not quite, because while fork doesn't actually take any parameters, a lot of other system calls actually do. So if you look at opening a file is a system call, and it takes some arguments. For example, you need to pass it the path of the file you want to open, and you need to pass it some flags about how you're going to open it. Are you opening it for read only? Are you opening it for read write? And so on. So what you're going to do is you're also going to, in this area here, you're going to load your params into registers A0 through A3. So we've set aside 4 registers, the standard 4 argument registers, to be used as the system call arguments. Now, if you need more than 4 arguments, which is totally possible, then what you would be doing is you'd make an array of those arguments and pass the address of the array through one of those registers. Then you raise the system call exception, and there you go. You have now asked the kernel to do a task. You've told it which system call you want it to execute. You've passed its parameters, and by raising the exception, you're forcing the kernel to run and handle that exception, which to handle the exception would be to do your system call for you. Now, what about return values? So we're going to leave the kernel part as a black box for now. And then we're going to come back and we're going to fill in that black box in just a couple minutes. Oh, yay, 2 black boxes. So, returns. So this is going to cause the kernel to run, and now the kernel is going to return something back to the fork. So after the syscall is raised. And we're actually going to return two values. So the kernel returns two values to the system call library. We return something in register V0, and we also return something in register A3. Now, what are we returning? So I always mix up which one gets returned through which. So V0 is either going to be the return value or an error code. Now, how would you differentiate between a return value and an error code? Well, this is actually why we need the second register for a return. And that is because you could say, well, error codes will be negative, but what if my function returns a negative value normally? Then that doesn't work. So what we do is register A3 contains either success or fail. Success being 0, fail being 1. And if it's success, then V0 has the return value, and if it's fail, then V0 has the error code. So there you go. That's how you cause a system call to run and how you get the values returned from that system call into your user library. And then in the library, it would interpret the results in V0 and A3, and it would handle that appropriately for the user program by returning a single value or actually throwing a software exception to the user program. So now we really need to inspect this black box. What happens in the kernel? So if you look on slide 20 here, you'll actually see a bit greater detail. So the application is going to call fork, which is the system call library function. Inside of the system call function, it's going to actually raise the exception. The exception gets picked up at the CPU, and the CPU is going to run the exception handler in the kernel. That creates the trap frame. And then we're going to realize, oh, this is a system call exception. So we're going to call a system call exception handler. The system call exception handler is going to look in register V0 for the kind of exception, or the kind of system call. And then we are going to look in, so then we're going to call the implementation of sysfork inside of the kernel. And then when it's done, it's going to return to the system called exception handler, which is going to format the output, and then we'll restore the trap frame, return from privileged mode back to unprivileged mode because we're done running in the kernel, where that library wrapper in the system call is going to take that 2-register output, turn it into a proper output for the user program, and then return the proper result to the user application. So there's a question on Twitch that says, is there a language level wrapper for this? For example, in standard lib, or do we have to implement this separately per architecture? Yeah, so implementing system calls is going to be specific by architecture. And what you tend to see in things like standard lib implementation, actually. So I was going to save this for another day, but if I can find it real quick here, which I probably can't. So this is the source code to Linux, by the way. Like the Linux kernel, that is. And I want to show you... You know, the truth is it probably doesn't matter which file I open, because you're going to see what happens in the Linux kernel, and hopefully that will actually help you understand what happens elsewhere. Actually, syscall, that might be a fun one to open. Actually, that was surprisingly boring. What I'm trying to find, by the way, is I want to kind of show you what it looks like to have code that runs on different architectures. Because many of you have probably never seen this before. And I'm not looking for self-tests. The organization in here is a little different than how our kernel is organized, so I had the file open a while ago, but admittedly I closed it. It's a lot of files to go through, but I do want you to see this because it's really neat. So doesn't help that I can't find the file I want. Locking. That's the director I want. So what I want to show you here is the implementation of a spin lock. This is the Linux kernel spin lock. No, I did not modify the file I opened. Okay. So this is the Linux kernel source code, and this is spinlock.c. Yes, the Linux kernel does have a spin lock. Every kernel does. So what I want to show you in here is that you'll see a lot of preprocessor directives. And if you actually investigate some of these preprocessor directives, a lot of them really depend. These are the preprocessor directives right here, right? So if these things are defined, then this lock function here will be defined. And if this is not defined, then you do this. So if you actually look in something like the standard C library, or if you look in the Linux kernel, you'll see lots of bits of code that are only defined for particular architectures. So when you're actually trying to compile something like the Linux kernel, or when you're trying to compile something like the standard C library, you actually have to specify what architecture you are compiling for. And that's going to set certain flags equal to true, which is going to cause a certain implementation to be compiled as opposed to others. So a lot of times things like the standard C library and the Linux kernel, it's a compile time choice as to which architecture you are going to be compiling for. So for example, if you were compiling for a MIPS architecture, you're going to set MIPS R3000 to be your arch type. Like, you can actually do this at compile time. So if you're here, you can do something like GCC. You can set things like a 64-bit or a 32-bit architecture. And that's going to set certain flags that it's going to enable certain implement bits of code and disable other bits of code. So a lot of libraries like the standard C library actually have implementations built in for several different kinds of architectures. That doesn't mean they have every architecture specified, but they do have a lot of the major ones. So yes, does the system call library, is your implementation architecture specific? Yes, but usually a major library, like for the standard library, is already going to have all of the implementations for all of the major architectures already built into it, and it's just a compile time flag that you set to specify which architecture implementation you are using. Yeah, details. We will look at the Linux kernel code another time. We're not going to go into great detail about that today. All right, but let's look in OS 161. So we've done the high level, what's going on here. And we could talk about things continuing in the notes, but I want to actually show you. So we're going to skip these slides here, 23, 22, because I think it's more valuable to actually show this to you than to talk about it. But before I do that, there is one more thing we do need to talk about, and that is stacks. So we've kind of told you that every thread has one stack, and that for OS 161 isn't entirely true. Every thread actually has two stacks in OS 161. Here's the idea. If you're a user program and you're running some stuff in user mode, and you put your stack frames on your stack, and then you make a system call, and the system call needs to put its stack frame somewhere, are you going to put the kernel privileged kernel data on the same shared stack with that user thread? It's probably not a good idea for two reasons. Number one, it raises the potential for a security breach where kernel data is now accessible for the user program. But number two, let's suppose that your user program takes the stack within like four bytes of overflowing, but would never actually overflow it. Well, then the kernel sharing your stack would overflow it and would cause a problem when the user program didn't actually have a problem. So each thread in OS 161 has two stacks, one for kernel and one for user. And the only thing that goes on the user stack is things where we are running in user privilege. So trap frames running kernel privilege, they're going on the kernel stack. Always. All right. Now I'd actually like to show you these things. So I'm going to start opening up some source files. And some of these source files you're going to find very useful for you when you're implementing assignment 2 shortly. All right. So, oops, I didn't want to leave kern. So we are in the kern directory. We are going to go into Arch. And then we're going to go into MIPS. And then we're going to go into locor. And then we're going to open exception1 or exception-mips1.s. That's an assembly file. Ooh, assembly, right? Don't worry, you don't have to write any assembly for this. I don't remember what line this is defined on, but there we go. On line 104, you'll see this function called common exception. This is the exception handler that runs when the kernel receives an exception or interrupt. And you'll see it, first thing it does, it's going to check if we were in user mode or privilege mode when the exception was raised. And if we were in user mode, then the first thing that it's going to do is it's going to find the kernel stack for this thread and switch to using the kernel stack. So that's what you're seeing happening here. If you are already in kernel mode and you can have an exception raised or an interrupt happen while you're already in kernel mode, then we already have our kernel stack in use, so we don't need to get a new kernel stack. Once you've got the kernel stack, then you're going to save the trap frame. So here's all of the assembly code responsible for saving the trap frame. So we'll save the trap frame, save the trap frame, and then we even grab the low and high registers and we save those as well. And then we're going to save the exception context. So all of the register values that were telling us why there is this exception happening. And this can be things like registers on the coprocessor. We're going to save all of that. Save it all to the stack so that when we actually run the specific exception handler, which we'll do next, we can actually figure out what happened and which specific exception handler we're going to need to handle that case. Then what we're going to do, you'll see, is we do jump and link MIPS trap. So we're going to jump to this MIPS trap function, which isn't actually in this file. Now, when MIPS trap actually returns, that is, the exception has been handled, you'll return down here, of course, in the exception return block, and this is where you actually restore the trap frame. And then at the end of this, you'll see RFE, which is return from exception, and RFE is going to actually switch the CPU from kernel mode back to user mode. All right, so now we're going to go into trap.c and look at MIPS trap. So MIPS trap takes a pointer to the trap frame. So they've actually encapsulated the trap frames in a structure here, but it's just a pointer to a place on the stack, really. And what's going to happen inside of MIPS trap is we're going to figure out what kind of exception actually happened. Now, something I haven't mentioned, but I do want to mention it now, is that at the point where the exception is raised on the CPU gets the exceptions turned off. And exceptions stay off until we figure out what kind of exception actually happened. And then for some exceptions, they may stay off, and for other exceptions, we may turn them back on again. So for example, if we are an interrupt, like truly this was a hardware interrupt, we're actually going to leave interrupts and exceptions off on the CPU. And we do that because we want to ensure that an interrupt is handled as quickly as possible. And it can't be handled quickly as possible if it's getting interrupted. So we're going to leave interrupts off until we handle this interrupt. And then the interrupt handler, the specific interrupt handler, will probably re-enable those interrupts before it returns. If, however, we are not an interrupt, then we don't consider ourselves to be that important, and so we are going to actually turn all exceptions and interrupts back on. So from here on out, our kernel code could actually be interrupted. Now, the one that we care about is it a system call? So if it's not an interrupt, then we're going to ask, is this exception actually a system call? And if it's a system call, interrupts are on, and we're going to call the system call dispatcher. And the system call dispatcher, let's actually show that because this is a file you're going to need to edit. So in not low core, but in the syscall directory, so one up, you'll see a file called syscall.c. And in here, this is the system call dispatcher. So what happens is you're again passing the pointer to a trap frame, and we're going to get the call code out of register V0, which is stored in the trap frame. And then we have a big old switch. And the switch is based on the call number. And we are going to call an appropriate handler depending on which kind of system call we've actually made. So for fork, we'll call sysfork. For wait PID, we'll call syswait PID, and so on and so forth. Now you're going to need to add a lot of things and modify this a lot because it's missing some things. But this is where the system calls actually get made. Once you've implemented the system calls, executed those, the return values are stored again in V0 and A3. If it's a success, we put a 0 in A3 and the return value in V0. Now this is in the trap frame. Why are we putting the result in the trap frame? Because after handling the system call, the trap frame will get restored to the CPU, so the return values will be restored to those proper registers. If, however, the system call resulted in a failure, we put 1 in A3 and an error code in V0. Now, this is a weird line. So when the CPU receives that exception, it doesn't advance the program counter. So to make sure that the system call exception doesn't get raised over and over and over again, we actually have to increment the program counter manually. So you'll see here we're incrementing the program counter manually so that we don't repeatedly raise the system call. And that's it. This returns to MIPS trap. MIPS trap returns to common exception. Common exception will restore the trap frame. It will go back to using the user stack, and then it will go back to user privilege, and interrupts are on still, and we go back to running the user program. And again, syscall.c, you're going to be editing a fair bit. So that's what actually happens when you do something like fork, which raises an interesting question. Something that you need to be very aware of if you're trying to write highly optimized code is how many system calls are you actually making? Because everything from print is always a system call, opening a file is always a system call, forking a new process is a system call. Even malloc. Mallocs don't guarantee a system call, but they can be a system call. So if you're trying to write code that's very efficient, you want to reduce the number of system calls. So there's this old problem, if you wanted to print the numbers from 1 to 1,000,000 onto the screen, which is faster? Having a for loop with a printf in the middle, or creating a character buffer that contains the numbers from 1 to 1,000,000 and printing that once. Which one is faster? And the answer is the one that doesn't have 1,000,000 prints, because it doesn't make 1,000,000 system calls. By the way, I have actually written that code before. First time I wrote that piece of code, it was for Commodore 64. And to print the numbers from 1 to 1,000,000 in that way, it actually took 12.5 hours. Yep, 12.5 hours. It was the 90s, though, early 90s. So what did you expect? Only takes like less than a minute now to do that. All right. So you've seen all of the code there. One last thing to talk about before we do some examples here is this concept of multiprocessing. So as you already know, each process can have multiple threads, but your computer can actually run multiple processes. And each of those processes, is going to share all of the available resources. So what's interesting is that if we're trying to do context switches between processes, well, we're not really doing context switches between processes. What we're doing is context switches between the threads, because it's not the processes that run, it's the threads that run. All right, a question on Twitch. If you get an exception or interrupt while it is executing an interrupt handler for the ones where exceptions are turned on, will the last executing handler be lost? No, actually it won't. And we're actually going to go through an example of handling an exception and getting an exception in just a minute. So hopefully that will answer how that works in a minute. So just to show you what happens when you have multiple processes and how they would share the CPU. So let's suppose our scheduling quantum is 15 units. And our timer goes off every 5 units, because that's usually how we do it, is we don't set the timer to go off at exactly the scheduling quantum. We usually set it to go off at a smaller number. So suppose process A is running. So process A has a thread, and it is running. There's a timer interrupt. So we go into kernel mode, and the kernel realizes, okay, your quantum hasn't expired. So that thread goes back to running. Goes back into kernel mode on the next quantum expired. Finally, once the actual scheduling quantum has expired, we do a context switch between threads, but those threads now belong to different processes. So it's really the same idea as before, except we're saying now the threads actually belong to different processes. So that's kind of interesting. All right. So now I want to do this example of looking at what happens on the stack for these system calls and interrupts. So we're going to start. We've got a kernel running in privileged mode, and we've got a bunch of processes running in unprivileged mode, and we know that. So process 1 is running, and on its user stack, you'll see it's got its application stack frames. And it's going to execute fork because it wants to fork a new process. So that's going to cause the system call library version of fork to run. So that goes onto the user stack. And then the code that fork is going to execute is it's going to load the system call code into register v0 and then raise the exception via syscall. When that exception gets raised, the CPU starts running common exception, which lives at this address here. We don't expect you to have that memorized, by the way. And the first thing it's going to do, of course, is switch to privilege mode and disable interrupts. And then it's going to save the trap frame. Once it's saved the trap frame onto the kernel stack, it's going to call MIPS trap to figure out what exception just got raised. So inside of MIPS trap, we realize, oh, it's a system call. So we turn interrupts back on. And then we're going to call the system call dispatcher. Inside the system called dispatcher, we realize that this is a fork operation, so we call sysfork. So we're happily executing sysfork, and then there's a timer interrupt. And this can happen, of course, because interrupts are on. So what is the consequence? What happens? Well, common exception runs again. Except common exception this time realizes, oh, we were already in kernel mode, so this is already the kernel stack I'm using. But I'm going to disable interrupts again until I figure out what's going on here. And I'm going to save the trap frame. You'll notice here it goes onto the same kernel stack as before. Then after saving the trap frame, it runs MIPS trap. MIPS trap says, oh, this was a timer interrupt. I'm going to call main bus interrupt, which is handling hardware. Main bus interrupt is going to then call the interrupt handler for the clock. And then the clock interrupt handler is going to call thread yield and thread switch and then switch frame, which is going to cause us to switch to a different thread from a different process. Because right now we only have processes with a single thread. And so what we're going to have happen over here is all of that saved on that kernel stack. This new thread from the new process is going to return from the switch frame, return from thread switch, return from thread yield, return from the interrupt handler, return from main bus, return from MIPS trap, finally restore its context from the trap frame, and then it's going to do return from exception, which is going to cause it to go back to using the user stack and running in user privilege. So that's going to cause us to go back to now process 2 is running. Now, what's interesting is all of that execution stack from running the system call and then getting interrupted from executing that system call, that's all saved on the stack of that thread from process 1. And that's interesting because what that means is when process 1 goes back to running, we'll return from the system call to the point where we were executing sysfork. We'll finish sysfork, and then we will return from that system call. So all of those, the interrupted exception is saved. Its state is saved so that when we go back to executing that thread, we can complete the execution of it. So nothing gets lost. Now, what would happen if we didn't have that lovely little interrupt in the middle of sysfork? Well, pretending that timer interrupt didn't occur, when system fork is done, we'd return to the system called dispatcher to set up our error codes and increment our program counter as appropriate. That will return us to MIPS trap, which will return us to common exception, where we'd restore the trap frame, switch back to the user stack, and then, using RFE, we'd return from exception, which switches us back into unprivileged mode, where fork in the user land would end up with the return values from sysfork, and it could handle them and return those to the user program. So there you go. That is how that actually works. Now, one thing I want to remind you is that even though we don't have final exams or midterms or things like that, we do have a final assessment, which is a quiz on Learn that will be available during the exam period. And questions about what order do things happen on the stack are pretty common, okay? So make sure you understand what these stack diagrams are actually doing. Now, there's one last thing to talk about in processes, and that is the concept of inter-process communication. So processes, as we've said numerous times, are isolated from each other and they can't communicate. But they need to communicate, and there's many good reasons why you might want them to. So, for example, many years ago, one program that I was working on, I actually needed the Vicon motion capture system to send data to Unreal Tournament so that I could see, so my actors were doing their acting, and they could actually see in real time in the game their characters being controlled. So those was 2 separate processes, and I need them to, one needed to receive data from the other. So how can you actually achieve this? Well, there's actually lots of easy ways to do this. One of the easiest ways that you can send data from one process to another, it's also very naive, is to use a file. So have a file that is opened by both processes and have them read and write data from it. course, you're going to have some synchronization issues here. For example, the process that's supposed to read needs to wait for the process that's writing to be done writing before it does the read, or you end up with some problems. So that's one thing. But using a file to have communication between processes is absolutely one way that you could do it. Another similar way you could do it is this concept of shared memory. Now, the idea of shared memory is that you're going to create a shared, so they each have their own separate address spaces, but you create a separate memory that they can both access. So it's kind of like an extra address space that they share. And they can both read and write to it. And then the idea is that, one process can write or one process can read and write to it and the other one will read. And again, you end up with synchronization problems because you don't want one process reading before the other process is done writing. So there's lots of other different ways that you can actually do interprocess communication, files being the absolute easiest way to do it. Shared memory is fairly simple to do as well. But something else you could do is pipes, where we send data from in a unidirectional way. So one process is writing and one process is reading. And it's going to be through an operating system managed buffer. So the OS is actually going to have a buffer that manages the path, the data flow from one process to another. System calls, again, are going to be used here. Similarly, you've got a message passing queue, which again is a kernel-managed data structure where it's going to manage data going from one process to another. And a final approach, which is the approach I ended up using, by the way, for my program, is to use the network. There are some advantages to using a network. For one, your two processes don't even have to be on the same computer, which was our problem, is because our computer running the Vicon motion capture software couldn't also run Unreal at the same time. So we actually had them running on two separate machines, and the two programs were communicating over a network. So you could create sockets, and you can then just grab data from the socket. That's actually quite easy. So it is possible for processes to communicate with each other, but in order to do it, you have to involve the kernel in some way. And yes, even with files, the kernel is involved because obviously in order to read and write a file, that's a system call. So processes can't directly on their own share data, but with help of the kernel, they can share data. And again, it does come down to some interesting synchronization problems. Some really interesting synchronization problems. All right. So this is actually the end of the processes section of the course. Now, normally I would give a lot of hints about assignment 2 here, but since I'm not actually sure anyone has started assignment 2, because I'm pretty sure, I don't remember when assignment 1 was due. Let me just check here. Considering assignment 1 isn't due till Friday, probably no one's looked at assignment 2. So we're not going to talk about assignment 2 today. We're just going to end things early. And in our next episode, we're actually going to start a new topic, which is virtual memory. Exciting, right? All right, so we will see you on Thursday then.
Oh, hi, Gary. In the middle of something?
No,
Check this out. Huh? Huh?
wow. Who did this? Josh or Venkat?
Somebody, yeah. Think you can use it?
Yeah, the compression is awesome.
Look at that. Oh,
Structure's perfect.
yeah. Oh, God. Oh, so much fun. Love doing this.
The governor of Missouri has called upon the president to declare a state of emergency. In local news, a tragic car accident took the life of Portland area computer software entrepreneur William Subb, a computer science graduate from the Massachusetts Institute of Technology. technology and a genius in his field, Sup